So yeah, thanks. I'm Denis Mazzucato, and today I will present my work at ReLU's product of absolute domains for fairness certification of neural networks. A work I published with Caterina on SAS 2021. And thanks for these COVID time papers in person, I'm able to present it here today. So without further ado, let's talk a little bit about the social impact of machine learning. So nowadays, it is increasingly being used to automate decisions that affect our lives. For example, we have healthcare systems, criminal justice, human resources with this recruiting pipeline. And so we want this software to not be biased against any subgroup of individuals. Furthermore, even regulation authorities move towards this direction, such as the European Union, which proposed this Artificial Intelligence Act about 1.5 years ago, with strict requirement for artificial intelligence programs and for fairness of machine learning systems. So there is a need for a tool to check the presence or the absence of bias in neural networks. And so here, in this sweet spot, I present our tool, Libra, which is a static analysis tool based by abstract interpretation. So Libra takes as input a neural network, and which category of neural network we use the same as basically the previous talk. So I will go a little bit more quick. We use feed-forward neural networks with ReLU activation. Feed-forward because the structure of the network is feed-forward left to right from an input layer to an output layer, and in between a few hidden layers, and where each neuron, the computation of each neuron apply is an affine computation of the neurons in the previous layer composed with a ReLU activation function, which is nothing more than the maximum between the output of the affine computation and 0. When we refer to only the output of the affine computation, we call it the pre-activation status of the neuron, and we refer to it with the little hat over the neuron name. So our network are used for classification purposes, which means that provided an input on the left, we classify the input as the index of the output vector, which yields the maximum value. So going back to Libra, as I said before, we want to check fairness more in detail. We want to check dependency fairness, which states that the classification outcome of our network is independent on this value of the sensitive features. Let me make it a little bit more clear with an example. We are in the setting of a recruiting process. So we have this network to do a first screening of candidate curriculum before a manual check. And so we have our sensitive feature in this case is the gender of the candidate. So we give the curriculum to the network, and we say that the network is fair whenever the same curriculum that only differ on the gender is categorized either as rejected or accepted. And we say that it's unfair when this doesn't apply. So when only changing the gender will also change the outcome. In that case, the network is not fair for gender. So going back to Libra, another input of our tool is the specification file, which you can specify the range of the input. So maybe you don't want to use the whole input space, or which feature is the sensitive one. And in this case, I show you a little network, don't really focus on the details. We only have 2 inputs, 2 outputs, and a bunch of other network in between. But and this will be used for the analysis later. So in such case, the specification file will specify that among R2, so the whole input domain, our input space will be only between 0 and 1 for both axes. And that X01 will be the sensitive feature. As I showed you before, it could be maybe the gender. So the first module within Libra is the front end, which is we generate the control flow graph from the network and handle categorical features. Then we have the engine, which is 2 iterators, a forward and then a backward one, which is also parameterized by this configuration budget, which I explain in a few minutes. So let's go inside this engine. We have a cheap forward pre-analysis by abstract domains, and after to do some partitioning, and after we have an exact backward analysis using the polyhedra domain. So the forward iterator propagate the input space through the network via abstract domains. And if we are already able, after the forward pass, to infer that only one possible one output is the only possibility, it means that the network, the input space is already fair, because in this case, no perturbation can change the outcome, and so not even perturbation on the sensitive feature. But this is unlikely to happen. Usually, we are interested in the activation pattern of the network, and so in the information of which pre-activation is always positive, always negative, or uncertain. We say that a neuron is always negative if the pre-activation is always negative, meaning that the maximum between something always negative and zero is zero. The dual is always positive because the maximum of something that is always positive and zero is always itself. So it behaves like the identity function. And otherwise, we say that is uncertain. The first two are the fixed activation status. And so we count these uncertain nodes. And if they are greater than our budget configuration threshold U, we partition. And how we partition? We split along any non-sensitive feature, and we continue the forward analysis. Whenever the number of uncertain nodes is below U instead, we say that the partition is feasible. We stop partitioning, and this partition will be ready for the backward iterator. But if the number of uncertain nodes is still greater than our threshold U, and the partition size becomes smaller than the other threshold L, we exclude the partition from the analysis, and we are not able to conclude anything on this partition until a more broad budget will be provided. So let me recall the example of before. We are going to run the forward iterator here. As budget configuration, we have L, which is the size limit 0.25, and the upper bound number of uncertain neurons, which is 2. So here the input space is 0101, and what abstract domain we are going to use? In my opinion, the most easy one, the interval domain. In this little portion of network, I briefly explain how it works. So we have two intervals, one for X and one for Y, and we have two weights A, B connecting X, Y, and a frequency efficiency C. So the formula to compute the pre-activation Z is this affine transformation, which can be easily done in interval arithmetics, provided that X and Y are intervals. And we have another interval where Z ranges. And then we have to apply the nonlinear ReLU activation function. How we do so? Since it is just the maximum between the pre-activation and 0, what we do is here I show the graph of the max 0 and Z, where the Z is the x-axis. We just do the bounding blocks. So we just put the interval between 0 and the upper bound of the pre-activation. And this is the domain we will use for the analysis of my example. So let's move on. We have the input space x00, x01, and same for x01. We go through the network. I will not stop for computation details, but at some point we will reach the output. Here, they overlap, and so we don't have a unique outcome. And as I said before, we are interested in the activation pattern. In this case, as you can see, there is x to 0, which is always positive. And so we collect this information, but we have other 3 neurons that are uncertain, and 3 is greater than 2, so we partition. And we split alongside x00, since it is not a sensitive feature. We could not have done it on x01, and we have partition PAA, PAB. Again, we do the analysis. In this case, PAA only have one uncertain node, and so it's already feasible for the backward analysis, but the other needs a little bit more partitioning. So we have now PABA, PABB. We go again to do the interval analysis, and we have the PABA only has 2 uncertain, and so it is feasible for the backward analysis, but the other still has 3. What we do, we cannot partition anymore because we already reached the limit size on the x00 axis, and so we exclude the partition from the analysis. So after the forward iterator, we have 2 feasible partition and 1 excluded. We are now ready to do the backward analysis. But first, we also put together the first 2 partitions, since the activation pattern of PABA implies the one of PAA. So it's a subset. And so we can suddenly put together the 2 partition, and we run the backward analysis only on PF. How the backward analysis work? So we have for each feasible partition and for each possible outcome, we run an exact backward analysis using polyhedra to the network until we reach the input. Here, within each feasible partition, we take the set of polyhedra from each different outcome, and we first project away the sensitive features, then we check for intersection. If we don't find intersection, means that no possible perturbation on the sensitive feature will change the outcome. Otherwise, it means that exists a perturbation on the sensitive feature which was able to change the outcome, since we project away that axis before checking for intersection. And so I continue my little example. We only have 1 feasible partition with x20 and x11 always fixed. We start with the 2 polyhedra for 1 output, meaning that x30 is greater than x31, and the other x31 greater than x30. So we do the affinity computation easily backward. But here we have x20 was always positive. So it behaved like the identity function. So I just propagate backward 1 more step the 2 polyhedra. Instead, x21 is nonlinear, is the maximum between the pre-activation and 0. So we need to split, and we do so. Again, likewise for the first layer, and we reach the input. Here, this is the result of the backward analysis. So first, remember, we arrived from PF. PF was not the whole input space, but was just without the part from 0.75 to 1. And here, we project away x01, and we obtain for the outcome, the red one was x31 greater than x30, and the other for x30 greater than x31. Now, clearly there is intersection between k and 0.75, and so definitely there is bias. So the analysis result is that we have a partition PAB, which we cannot conclude anything, but from x000 to k is definitely fair, and from k to 0.75 is definitely biased. And last but not least, we have the abstract domain pool, which is composed by the interval domain, symbolic, deep poly, heurify, and a newly introduced product builder to combine all of them above. So we go briefly through the 3 most interesting ones, since Box already explained it. So here in blue on the left, we have the triangle approximation, which is the best approximation for a single ReLU, and how symbolic approximate that the ReLU function with the bounding box, and propagating a symbolic invariant. The poly instead change the lower, also propagate 2 symbolic equations. And the lower equation is decided between 2 options. One is ReLU x greater than x, and the other constraint is ReLU x greater than 0, depending on which one minimize the area. And instead, heurify minimize the error, again with 2 equations, but this time for bounds. And so we try a few experiments on that, and we see that there is not a clear winner. So for different budget configuration, we have different winners. And so we introduce our reduced products that is going to share bounds and achieve the tightest invariance before computing the ReLU approximation. And here in the portion of networks, as I showed before, we have X and Y that has some invariant in their respective domains. So we have the symbolic for X, the poly for X and unify for X, and likewise for Y. Now we compute the pre-activation Z within the respective domain, but now we have to apply the ReLU function to compute Z. How we do it? Before we do it, we share the most tight bounds. So for the lower bound, we take the maximum between all the lower bound and the lowest lower bound of Neurify. Instead, for the upper bound, we take the highest upper bound of Neurify and the upper bound of the symbolic and the poly, and we take the minimum of them. And this invariant is the most tight interval for hat Z. How we go back to the three domains for symbolic, it's easy because its invariance is just 2 bounds. Same for the poly, we put the most tight bounds there, but Neurify needs 4 bounds. So how do we fill the 2 bounds in between? So we take the highest lower bound of the pre-activation of Z, and the maximum between that and the just computed lower bound, and same for the for the lowest upper bound, we take the minimum. And so this is the invariant that is propagated by our domain, that is shared by our reduced product. And as you can see from our experiments, we show that the product domain, which is composed by the product of symbolic, poly, and Neurify altogether, it's the one that is achieving the highest cover for all the configuration. And so this concludes the analysis of Libra. But since it was a talk I presented a year ago, let's say, I also want to speak a little bit more about the ongoing work. So here there is the network I showed before, and there is an easy translation to, let's say, program Python kind syntax, which is this one. And here, since we have we can run canonical analysis we find in literature. For example, if we run the input data usage framework, we see that there is some kind of relation between saying that X01 is unused, meaning that the same network X01 is fair. It's similar because I need to add the output of the classification, and in this case, they are equivalent. And the two analyses are equivalent. And so, how we want to proceed now? We want to extend this input data usage framework data science programs, since a lot of on huge dataset, and maybe they use all the variables in that dataset, but maybe they only use just the beginning of the dataset and not like the rest, and only slightly using the rest. And so we can give suggestion to developers how to repair the program. And so yeah, that was what we are trying to do now, to achieve now. And so yeah, just realized I'm 5 minutes ahead, but more time for questions. Thank you.
Thank you. Questions? Hey, sorry, I probably missed this, but is it possible in your tool and your theory to push just the gender, for instance, of a person through the network and leave everything else unspecified?
Sorry, what do you mean by pushing gender?
So you have this forward analysis, right?
Yeah.
There, could you specify something like abstractly a person has that gender, but everything else about the application you were saying something about the recruitment process, right?
Yeah.
So you leave everything else abstract and specify just the gender. Can you do something like that in your?
So we concretize one input specifically for the gender, and we and we leave the rest unknown, and we do the same analysis. Is that what do you mean?
Maybe.
Oh, it's like removing the input and leaving like a parameter. And so in that case,
So the question is, could you then compare when you push male and female and others through the network and then compare what the outcome regions are, whether to accept or reject the application?
oh, I'm not. I don't really know what means pushing a feature to the network, but I will try to answer anyway. I think what we do is trying all the perturbation in all the input to see if the variables. I think if you think about the relation between unused variable, it's like checking if the gender is unused. And so we want that every perturbation of gender will never change the outcome, no matter what the other outputs, inputs, sorry. So fixing the output, the input we want to change, it doesn't really. Yeah, I don't think we will be able to do something there because we are basically fixing the input we want to perturb. Maybe yeah, has more sense to only perturb the gender. In that case, for a specific input, we would be able to say that it's fair, but it's way more easy.
So yeah, I think the idea of me was to look only at the gender and see whether you can tell whether this has any impact at all.
Look only at the gender and see.
We can discuss this as well.
Oh, we have time.
Oh, yeah.
No, but not so much.
No. What you mean is that you abstract all the other inputs, so that you set to top all other inputs and you just leave gender, female, and you see what you get out of the output. I think that would give you a very approximate output in one case or the other, and so you cannot conclude. I don't know, we have tried. So, I don't know if it helps.
Tom.
Hi, thank you for the talk.
Thank you.
Just a quick question on the fairness specification problem. Is there any way to handle more complex specifications than just this feature should not impact the result? Like, for example, if you have neural network that learns stuff about with two features like the racing and postal code, and even if you blind the neural network of the race, you can still use the postcode
Sorry,
as
I really have problem. I really have problem understanding the.
okay.
Maybe.
I'm too close to the mic. Okay. So, do you think there is any way to specify more complex fairness stuff than just this feature do not have to impact the result?
Do you have in mind any kind of more complex?
Yeah. Well, for example, imagine a neural network that between this feature race and postcode. And you train the neural network to not use the race feature, it can still learn that postcode is a good proxy for race.
Yeah, definitely.
So how do you specify this kind of stuff? Can you use that?
we actually rely on users to do a pre-analysis of the features, so to find which one they want to check for bias. But very, very easy way, it would be to brute force and try all the possibilities to see, to discover proxy features. But so far with our tool, we rely on the users to tell us like this feature, please check this feature for bias. So we don't do any input analysis to discover feature bias on other features.
Would you have any insight on how to find these proxy features more easily than just more efficiently than brute forcing the?
Added them with first. Yeah, let me think. That's a very good question. Because I never really think about it, but to find bias, maybe a way like with equivalence of programs that variable are not used, maybe you can, instead of checking that a variable is not used, you want an analysis that check which variable is not used. So maybe if we have with the quantitative analysis, I think we should be able to, probably with a version of a quantitative analysis, it should be able to quantify the use of a lot of variables, maybe all the inputs together. And then if you can give a bound to it, you can check which variable has a very, very low impact and then check the analysis only on those variables. That's an idea, but yeah, I never really give any more thought. Thank you.
For the three very similar questions, if anyone has any
Please do. No. Okay. So you.
Yeah, it was a similar question.
Sure.
For your application, if we have a good case in which we are given the correlations between the two variables, could you maybe use that to show ongoing?
Oh, yeah, so far we only accept specification which are box. We don't really, okay, if we have constraints between variable and the input, what we can do, I know there are a few works that solve this using a pre-input layer, which are a few ways that are kind of incorporating in the network these constraints, but yeah, that's a way more difficult. If you don't have a box, it's a way more difficult to do this kind of analysis at the beginning because we expect the invariance to be an interval. But yeah, then we can rely on a solver and then maybe lose a lot of scalability. And, yeah. Thank you.
Okay. We're done. Okay, we're at 3 times, so in the sense, speak again.